All right, let's get started today. So welcome everyone back to our last class, right? This is day 6 of Intro to AP Physics 1. And I just want to give a special thanks, kudos to all of you guys who came back. I know some of you guys had difficulties, things like that, but coming back to the last session is a very important and mark of your commitment. So today, we're just going to learn a little more about Intro to AP Physics. The AP Physics 1 course, since that's what you chose last time. Most of you chose that last time. And today we're going to end a little bit earlier because it's also our last class, and I think it would be easier for everyone if I just let everyone out a little earlier, like 15 minutes earlier. Okay, so let's get started. So last time, I just want to, before moving on to energy and momentum, I wanted to just do a practice question on gravitation and uniform circular motion. Because last time you guys said that you're really firm in like kinematics, but some of you didn't know, weren't very firm in dynamics. So we did a practice question together, and I think practice questions are very good of evaluating whether you're ready to move on or not. So let's start off with the question. The problem is, an astronaut on a space mission lands on a planet which is 3 times the mass and twice the radius of the Earth. What is her weight, which is W sub x, on this planet as a multiple of her Earth weight, W sub e? Okay, so we know, how about you guys? Why don't you guys tell me, how should we start off this problem? First off, just tell me which unit do you think we should start off with, which equation we should use, and how would you approach this problem? Artie, we're not doing Kahoot today, but if you guys want to practice a Kahoot from last time, we could do that. We're just letting out everyone earlier today, and I'll have something to address at the end too as well. All right, so continuing, does anyone have any idea of how we're going to approach this problem? How about just tell me which unit do you think this problem would be in? The goal says, understand the effect of a planet's mass and radius on the weight of an object on the planet's surface. So the term mass, radius, weight, planet, which kind of unit do you think we're talking about? If you guys have no idea, we're actually using the unit gravitation and uniform circular motion. The reason why we are doing this is we're not using kinematics, right? Kinematics deals with velocity, acceleration, displacement, distance, things like this, right? But we're talking about mass here, right? You see mass and radius. Dynamics, they deal with force, mass, and acceleration, right? And forces, mostly forces. But you see the term radius here. So you can eliminate kinematics and dynamics because you're not going to use them, right? You might say dynamics because you see mass, but dynamics doesn't deal with radius, okay? So when you see radius, you know it's definitely got to be either a uniform circular motion problem or a gravitation problem for now, okay? So we just determined which unit we're going to be using to solve this problem. Now, which equation do you think we should be using to solve this problem? Just testing what you guys learned last time. We only learned one equation for gravitation and uniform circular motion. Yeah, exactly. Yeah, Fg equals big G, right? Times n1 times n2 over r squared, right? This is the only equation we have ever learned for gravitation. All right, so let me just draw this on, right? Brian said FG equals big G times M1, M2 all over R squared. Okay, now since an astronaut on a space mission lands on a planet with 3 times the mass and twice the radius of the Earth, right? So the way I would solve this problem is write out everything I know about the Earth and everything I know about this new planet that they're talking about, right? So let me just write this out, Earth, planet X, right? And the problem tells us that that this new planet, planet X, has 3 times the mass. So I would just say 3 times mass m sub e. M sub e just means the mass of the Earth, okay? And it has twice the radius, so it would be 2r sub e, right? And then for the Earth, it would just be m sub e and r sub e, right? These are just variables, actually constants to denote what we're talking about. So we don't have to write out the entire number. We can just call it as a variable. So now it asks us, what is her weight delta x, no, sorry, not delta x, w sub x on this planet as a multiple of her Earth weight w sub e. So when they're talking about multiple, it's most likely they're asking about a factor, like is this like a ratio, a factor? So how do you, does anyone have any ideas after I've written all the givens out and the equation we're going to use? Does anyone have an idea how we're going to solve this problem? W sub x is just weight, and that's equal to Fg. So people do like W, that's really just Fg. But there's two Fg's, right? There's Fg on the Earth and there's an Fg on planet X. So does anyone want to give a stab at this problem? Anyone have any idea? It can be wrong. Just I really enjoy if you participate or you're willing to give this a try. Okay, so I'm assuming no one has an idea. Well, the way you would solve this problem is, remember last time we got Newton's universal law of gravitation, right? Fg equals g, right? M1, M2 over R squared, right? And then we derived the equation for mg, right? Before in the first class, I remember I told you, you guys talked about 9.81 meters per second squared, and we were actually able to calculate that, right? We got Fg equals mg, right? And the way we derive this equation is through substitution, right? We substituted the values I gave you on this slide and you put it into the equation to get that 9.8. The same thing works in this equation, except it's not actual numbers like 9.81 meters per second squared. They're actually variables like 3me, m sub e, right? So the same way you'll solve this problem is by substituting these values into this equation. So you actually, you know, like when we find a ratio, right? It's usually a fraction. So if I say this person is 5 times as heavy as me, it would be 5 over 1 because the 5 is the mass of that person. I mean, the ratio of that person's mass to me. So if I write 5x over x, right? X is my mass. 5x is saying that that person's 5 times my mass, which is x, right? You would get 5, and that's your ratio. Same thing here. What you're doing is you're doing Fg x over Fg of the Earth, okay? And FGE is just the same thing as W, and FGX is just the same thing as W sub x, because weight and force of gravity is the same thing. So since I gave you this idea already, now I would like you guys to try and solve this problem on your own, and see if you guys could manage this problem. So again, if you have any questions, let me know. And I'll just leave the rest of the time for you guys to solve this problem. Right, we're taking the ratio of this force of gravity on planet X over the force of gravity on the Earth. And Fg, right, is equal to this equation. So you'll basically be doing this equation over another of this equation, but the variables would be different because the radius and the mass are different. Does that make any sense? I'll go over the answer later, but I believe you are correct. Just remember your units because that answer is relative to a variable, right? It's not a constant. It's relative to some variable. All right. Anyone else want to give it a try? How about this? You guys want to be put into breakout rooms, like into smaller groups, and talk on your own. If you guys don't want to talk as a big group, would you guys like that? Okay. Either way. Okay. So I'll just put you guys in breakout rooms, and I'll put around how many? Oh, we have 19 participants. I'll put let's put 6. All right, in one group, and we'll come back with the answer. All right. You guys have any ideas? How would you solve this problem? Anything? Okay, I'll give you a hint. Basically, we learned from the uniform that equation Brian just said, right? Um, Basically what you would do is, there's M1 and M2, right? But last time when we derived the equation for mg, right, we left the m on the side. And that's because this force is relative to that mass, right? As the mass increases, your force increases. So the same thing is what you do uh, on the FG equation, right? Because you have FG equals G, big G times M1 times M2 over R squared. But your R is 2 R sub E, right? And your mass is 3 M sub E, right? So you have a 3 M sub E times M over the square of um, over 2 R sub E squared. So after you simplify that equation, that gives you the ratio. You guys understand? It's like saying, um, this person is right 10 times heavier than me. And let's just say to find the weight of a person, you have to take his proportion of the length times his width times a constant. Okay, let's just make this equation up, right? So the constant is the same, right? That's like big G, but his mass, no, his width and length are, let's just say, twice the width and length of me. So what I would do to solve the ratio is basically do 2 times my mass over using that equation, basically substituting those variables in. All right, you guys understand? Um, I'll discuss more about it in the big room. All right. Oh, nice. You guys are using the whiteboard. Do you guys need any help? Yeah. All right. So let me just annotate really quick. So before, right, we did this FG equals big G, right, times M1 over M2 over R squared, right? And we know that the M, right, when we derived mg, right, we put one m on the side, right, because it's relative to the mass. So what we do here is the same thing. This will be fgx, and we have an fg of the Earth, right? G m1, m2, sorry, there's m3, over r squared. Okay, that's really weird. Over r squared, right? But instead of having m1 and m2, we have me, right, and re, right? And for fgx, we know that it's 3me and 2re. So what you would do is you substitute this into m1, and you substitute this into the r, and then you simplify to find your ratio. When you substitute all this into this equation and you find that fraction, that will be your answer, because that's like the ratio. All right, does that help? Okay, the numbers in the front are, have you ever learned about coefficients? Like in algebra, a coefficient like 2x plus 1, that y equals 2x plus 1. Yeah, so the 2 in front is a coefficient. It's basically like a factor. You're taking x and timesing it by 2. Same thing in here, right? They told us that the mass is 3 times the mass of the Earth. So what we're doing is the same thing. We're taking 3 times me. We're just not having a separate variable just for the mass of planet X. We're expressing the mass of planet X as 3 times the mass of the Earth, which is 3me. And the 2 is the 2 times the radius, because the radius is twice as bigger. All right, I'm going to join another room and continue your discussion and find out the answer as well. All right, did any of you guys come with any ideas, or do you guys need a little help? Okay, so let me just share on the whiteboard really quick. All right, when I talked in the big room, right, we talked about using the universal law of gravitation, right? Fg equals big G m1 m2 over r squared. And remember when we did that derivation to find mg from this equation, right? We use this equation to find mg by substituting those values in. The same thing happens in this equation. Basically, instead of having numbers, you have variables instead. So we have mass of x equals 3 times mass of e, and the radius, right, radius of x is actually 2 times the radius of e. So instead of having like, oh, r over x, r sub x equals 6 meters, right, we're having it as 2re. Okay, so what you would basically do is, remember we did a derivation with mg last time. We left one m on the side because it's relative to mass, right? Fg is relative to mass, and you don't know the mass. The mass can change, but you can find a relationship, which is why you need that coefficient 9.8. Similarly, in here, what you would do is you take 3me and you substitute it into either m1 or m2, and you take 2re and substitute that as the r. So when you do r squared, you're actually getting 4re. Does that give you some like sense of what's happening? So basically, after you find this equation, you would do again, this would be fgx, you would have to do fge, which would just be gm m1 times me over r squared. I'm sorry, r sub e squared. You take this equation and divide it by the bottom, and that would give you your final answer. All right. All I hope that helps. Oh, I'm so sorry, Artie. I didn't notice that. Um, I mean, we'll go over it together, so you won't miss anything out. Okay, so I'm assuming everyone came back in. Let's find out how we can solve this problem. All right, so you know when we did that derivation for mg, we did basically fg, right, equals g, sorry, this equal sign, m1 over m2 over r squared, right? For m2, we didn't know what it was because it's relative to mass, right? Your force of gravity increases relative to your mass. That's why if someone's heavier than you, they experience a larger force of gravity. So we can't actually substitute anything as m2. We just have to leave it on the side as m, right? Because it's like a variable. It's like 2x plus 1. You don't know what x is unless someone tells you what it is, but you can find the equation, right? But we do know what M1 is, right? M1 is equal to 3ME, right? And we do know what R is. R is 2M, sorry, not M, R, E. R is just radius, M is just mass, and E is for Earth, all right? So what we would do is we would do G 3ME over M over the square of 2R squared. That gives us FGX. Okay, so what is 2 to the square 2 to the power of 2? What is 2 to the power of 2? 4, right? So what we would get is G, right? This brings us over to 3 G M E times small m over 4 R E, right? However, this is not our final answer, right? Because there's so many variables, right? Things like that. We have to get rid of this. So what we do is we're actually taking the ratio, right? When we do the ratio, we do FGX over FGE, right? The force of gravity on planet X over the force of gravity on Earth. That gives you the ratio, the proportion between them two, right? So we write another equation, right? This is FG on the Earth equals G, right? M and E over RE squared. Okay, now we take this equation and we divide it by this equation. All right, so let's move this over to the side. And let's bring this up. So we get 3 M E G M over 4 R E, right? This entire thing divided by G M N E over R E, right? This thing. And let's clear all this. So why don't you guys try this out? Since I already wrote everything out, do a simple fraction division calculation and find out the final answer, right? I already wrote everything out. All you have to do is keep, change, flip, right? If you ever learn how to divide fractions. And Ali, I'll answer your question in just 1 second. Did anyone come up with an answer? Okay, I see a 3/4 in the chat. Any other answers? Okay, another 3/4. Okay, another 3/4. Okay, um, so I'll answer Ali's question first. So why she asked, why would you divide it though? Is it because they're multiples? So when when the question says, what is her weight W sub X on this planet as a multiple of her Earth weight sub W sub E? When they say a multiple, it's another word for just saying like a ratio or a factor, right? So if you learn about like multiplication, right, 2 times 2, 2 times 3, 2 times 4, they're all multiples of 2, right? And the same thing is between W sub X and W sub E. All right, so now let's just bring us back to the calculation. So we have 3 MEGM over 4RE, right? And that's divided by G over R. And what we do when we divide fractions is we keep, change, flip, right? Keep, change, and flip. So we keep this, right? And then we change this into a multiplication, but we flip this as a reciprocal. So it becomes RE over G small m big M E. And when we multiply fractions, right, we do numerator times numerator and denominator times denominator. So when you have 3 ME times G over M, sorry, not G over M, G times small m, you get this final fraction. All right, let me just write this out. So you get 3 ME small m, or E, right, and the denominator times denominator, and you get 4 R E, sorry, this is sub E, squared, because you have 2 REs, G small m, M E. Okay. So when you have a variable on the top and on the bottom, what you can do is you can cancel them out, right? Because it's like 1 divided by 1. You just get 1, you divide them out. So you get, divide this, you can cancel out, G cancels out, small m cancels out. RE does not get canceled out because you have a square on the bottom. So it actually is 3 over 4 RE on the bottom, 4 RE. That's your final answer. So many of you guys just said 3 over 4, you know. I was saying you have to include a variable because 3 over 4 is a constant, but it's relative to something, you know. It's not like just 3/4, right? If RE changes, it's not 3/4 anymore. Okay, so that's your final answer. Does anyone have any questions? And the bottom also shows you how you should have solved this problem. Okay, so let's move on to the next slide. Okay, so before you guys chose option 2, which was, I mean, last class you chose option 2, which was you know, going more into AP Physics 1 and not doing it practice, right? So the next unit after gravitation and uniform circular motion is energy. Okay, I think you guys might have learned about energy and like chemistry, things like that. But I would like you guys to put in the chat, what do you think energy is in physics? Like, why do we use energy? Or what do you think energy could be? Like, what forms of energy do you think we're talking about in physics? Yeah, and of course you can always look into the picture on the right. It should give you some idea as well. Yeah, kinetic potential. Okay, what other types of energy? Last time I showed you guys like a friction thing, right? A performance of like how we have sandpaper. Okay, gravitational. I like that too. Um, be more specific. Static. What kind of static? Like just static energy? Static energy, I don't think that exists, but if you add one more word in between, it does exist. Last time we talked about friction, right? How like if you rub your hands and then energy is lost because you're dissipating heat into the atmosphere, right? Friction itself is also considered a form of energy. And we'll talk more about that later. Okay, so I see a lot. Chemical, heat, elastic, thermal, nuclear, okay, nuclear, gravitational, static, kinetic potential. These are all great things. In physics, we don't, in AP Physics 1 to be specific, we don't talk about nuclear energy. We also don't really talk about thermal energy, though some calculations might have it. We don't talk about elastic energy as well. And we don't, I mean, we kind of do talk about chemical energy, but it's not very big in the course. It doesn't have a really big composition in energy. All right, so mechanical energy, that's a very good term. That's a very good term. So let's talk about this. So energy, you guys said thermal, elastic, heat. So for thermal and heat, they're basically the same thing, but basically in AP Physics 1, when we have a system where energy is being lost, we usually refer to either heat energy or sound energy, or even like, I think we just talk about heat or sound energy when we talk about a system that is open. Okay, what do you guys think is the difference between a open and a closed system? You can also think of it as like, what does it mean when a system is open? Or what does it mean when a system is closed? And how does that relate to energy, right? If I'm talking about a energy problem and I'm saying this system is open, this system is closed, what do you think is the difference? Daniel, I do like your hypothesis. Um, it's kind of close, but not exactly, but you are pretty close. Anyone else want to give a stab at this? Open circuit, closed circuit analogy? Yeah, definitely. Right? Circuits do deal with electricity, and electricity is a form of energy. Okay, so I'll just cut to the chase. Open systems refer to, okay, let's just start from the basic. When we talk about systems in physics, we usually talk about more than one objects, right? If I have two objects dealing that I'm talking about in a problem, it's usually a system. A system is composed of more than one object, right? If I just talk about this pen, right, and I'm talking about it falling to the earth because I drop it at some height h and then I let it go and it falls down. This pen itself is a object, but if I include the earth, right, because they're interacting, the pen and the earth is interacting together, then it becomes a system. And in physics, we solve problems through system approaches and object approaches. So when you have a system approach, we usually talk about using energy. If you're doing like an open system approach, we usually use like dynamics, like free body diagrams, things like that to help us, and kinematics. But if when we're using a system approach, we're usually talking about momentum, energy, things like that. Okay. So a open system is basically when you have energy flowing in, or it can be taken away. So basically, energy is not conserved in this system because I can add energy in or I can take energy out. An example of this is, let's say I have two hands, right, and I'm rubbing them together. This is an open system if I'm not including the atmosphere around me, right? Because the reason why is because I have energy, like a I'm not sure of the exact term, but you could just call it like bioenergy in my hands, right? My blood. There's heat in my hands right now. But when I rub them together, right, I'm generating heat energy. And when I let go, that heat dissipates into the atmosphere, right? So energy is actually being lost for me. And that's why you feel cold um, if you're in the winter or if you're in the snow, if you don't have a jacket on, because that jacket basically um, keeps your system, your body as a closed system because it insulates that energy so it doesn't run away. Does that give you does that help you guys understand what open and closed systems are? Okay, so yeah, okay. So closed system is the exact opposite. It's basically saying that this system is um, conserved. This energy is conserved from the beginning to the end. Okay, so energy can be transferred, can be converted in different ways, but it always has to be conserved in one way or the other. So I can have, let's say I have a car, right? And I press the gas pedal, right? It has chemical energy, right? The gas inside, it has chemical energy, right? It's just not being used up, but it does have energy, and um, that's the amount that starts off initially. And once I press that gas pedal, right, it converts the engine converts through combustion, converts the chemical energy, right, the gasoline into mechanical energy. It turns the motors or electrical sometimes, right, to start on the car, things like that. So the energy is actually being converted. However, um, the energy is not being lost because the car itself, as one system, is not losing that energy. It's just converting it into one way or the other. So it's very important when you solve AP Physics 1 problems that you know what to define your system as, okay? So let's say if I'm solving a problem with, okay, um, this problem asks me to um, find the acceleration of a pen that I'm dropping from a height h. In my system, if I do not include the earth, then um, most likely I don't have to include gravity. However, if the system does include the earth, right, then I have to include gravity. So systems are very important. They're also very confusing sometimes, but I would usually say like know the difference between open and closed systems, and that should help you a lot. Okay, work and mechanical energy. So basically I think in chemistry, if you learned chemistry before, they have the law of conservation of energy, right? It's basically saying the initial amount of energy that you have is the amount of energy you have at the end, right? Energy is not being lost. It's just transferred in one way or the other. That's the same way, but in physics, we call this law of conservation of mechanical energy. The reason why we say mechanical energy is because in AP Physics 1, we deal mostly with mechanics, right? Physical objects. We don't deal with electrostatic forces or electrical magnetic forces, things that you can't really see except for gravity, right? But everything else is basically visible to a human eye. Okay, so what is work? Work is kind of like force, except it's kind of like it's a term for energy. Um, Basically, okay, I'll just write the equation out. So work is actually this equation right here. Work equals force times distance. And basically what it's saying is if I have a bicycle, right, and I'm riding it for 10 meters, the amount of work that I need is basically the amount of force I need to apply to the pedals times the distance, the 10 meters that I traveled. So work is important because it's how we deal with energy, and it's really important that we learn about this. You'll see more of it in the future. Like, you know how we have like F sub S, right? That's force of, I'm sorry, F of G, right? That's force of gravity. We also have like W sub F, and that's work due to friction. So work is kind of like force, except it's more of like an energy point of view. It's like, how much energy do I need to accomplish this goal? And that's the work. Okay. You can also think of it as like you're running up a pair of you're running up 10 floors of stairs, right? The amount of work that you would need is basically the force exerted by your foot on each stair times the height of those 10 floors. You could think of it as that as well. So what is power? Power is basically work over time. It's kind of like acceleration, except it's more of like energy, but the rate of which work is being done. So if you have a motor, right, and it tells you the power of it, it's like um, 12 volts or something like that. It's basically saying that the amount of energy that's being released uh, is the work over the time period. So if I have like um, a 12-volt battery, right, it's basically releasing like 12 volts every second, or you could think of it as something like that. I'm not very familiar with electricity, but that's kind of like an analogy of what power is. And power is basically force over time. Actually, you could just say change in work over time. It's kind of like, think of it as like an analogy of acceleration and velocity. You know, like velocity is distance over time, but then like power, which is kind of like acceleration. If you could think of it, not physically like they're the same, but the equation is very similar. Okay, now we have PE and KE. PE is potential energy. It's basically how much energy do I have. You know, like sometimes things don't have to be moving, but they can still have energy, and that's basically potential energy. Um, KE is kinetic energy. It's basically when an object is moving, that energy turns into kinetic. So in this right diagram, right, you see this car on, sorry, not a car, this bicyclist, the cyclist, he's riding up a hill. When he reaches the height of his hill, he is not moving. He's instantaneously not moving. And all that energy that he used in the beginning, which is kinetic, turns into potential. And that's basically why, you know, like in the past in Mesopotamia, they had like the irrigation systems, things like that. That was ancient civilizations. They would basically have irrigation systems from large mountains, and they would dig them down to their civilizations, which were beneath those mountains. And the reason why is because they didn't have to have any like pump or anything, right? The water would just flow down like a river, and that's basically utilizing potential energy and turning that into kinetic energy to move that water into where they wanted it to go. In potential energy, we usually call it gravitational potential energy because potential energy can be in different forms, but the one in the right is gravitational potential energy. It's kind of like static friction and kinetic friction, but we have to specify which type of energy, potential energy we're talking about. Okay, next. Okay, yeah, this is also an image of what a open and a closed system is, right? Um, it literally says the definition: a system is a group of objects. A closed system is an energy is a system where the only energy transfer and transformation that happens involves mechanical energy. Energy is not transferred to objects outside of the system, right? If I talk about rubbing my hands and I'm only including my hands in the system, that if I don't include the atmosphere around, it's an open system because the energy is being lost. However, if I include the atmosphere around me with my hands, it becomes a closed system because energy is going out, but it's staying within my system. Does that understand? Does that help you guys understand things? This is a very important concept in AP Physics 1 because when you solve problems, you have to specify which system you're using and what is in your system. Usually in problems, they also tell you like a earth ball system, which is basically having the earth acting on the ball, and they're both within the same system. Okay, next. All right, so that is basically it for now. As I said, I'll let you guys go earlier. Right now is 2:45. And I just wanted to say that I really appreciate all of you guys for coming in to this class. It was really fun meeting all of you. And I hope you guys also learned something from this course. Don't leave yet. This is a feedback form that I will put into the chat. And basically what's happening is, remember last time in the beginning, I actually said I might make a continuation of this course, right? However, I will be doing a continuation of this course in 2 weeks. However, it will not be through Wave because unfortunately, I do have my own nonprofit, and we specialize in STEM activities. So we don't do like humanities, things like that. And in that continuation, we'll be building things together like a roller coaster or a spaghetti bridge, and we'll be doing competitions online. So it'll be really fun. I hope if you guys, if you're just interested in physics, like many of you are, some of you guys are still middle school students, um, you know, and or if you guys are in high school and planning on taking AP Physics 1 next year, I highly recommend it. Basically, what's going to be happening is I'll be basically simulating everything I've done in my year of preparation for the test, and basically teaching it to you guys. So you'll go through the exact same thing that I went through, and hopefully that'll help you get the 5 on the College Board test. So I just put it in the chat. And also, if you're interested in taking the continuation course, please just let us know in the form. And also, another special opportunity that I will be releasing is if you're a high school student. So right now, if you're going to 9th grade, even if you're an 8th grader right now, but you're going to 9th grade in this as of September, or if you're a college student or anything like that, we are asking if you would like to join our tech team, or the people who design all the courses or do like the the operations or logistics behind the team. It's a great opportunity. You will get volunteer hours, and you might also get paid as well. All right, so that's it for me. Please fill out this form, even if you don't want to continue. It's a feedback form, just letting me know how much you learned in this course. What do you want to change about this, and anything we could improve on. So if you guys have any questions, either physics or like just random questions, just ask in the chat, and I'll be the last to leave. Yeah, no problem. Oh yeah, and by the way, I'll upload all these onto these video recordings. So also on the YouTube channel that we have. So please subscribe if you haven't as well, and give us a like. Do any of you guys have questions regarding what I just said about uh, the nonprofit, or even about physics? Ariel, do you have any questions? If not, I have to do something soon, so I'll have to close this meeting. I mean, if you check, if you if you open the feedback form, my email should be in there. So if you have any questions, you can always email me. All right.